In this video, we're going to take a look at what is a set from a mathematical standpoint and define a couple properties that are associated with sets, just to get you used to the concepts and the terminology. So let's start with the definition of a set. So a set is a well-defined, and we'll talk about what this means in a second, a well-defined collection of objects. All right, so that is a set. And these objects, right, so these things that we're talking about, so these objects are often called elements, right, or members of the set, right? Now, so what do we mean by well-defined? So let me just give a few examples of these collections, right, or collections that they either are or aren't a set, right, or sets. So the first one, it could be, let's just say, all warm days in 2019, right? So the question is this a set or not? So all warm days. Well, to determine if a day is a part of this collection or not, we would have to know precisely what we mean by warm. Now, is warm 80 degrees? Is it 85 degrees? Is it 90 degrees? Is it 75 degrees? So warm in itself isn't clear. It's not clearly defined. So I can't determine all the days in 2019 that are, I'll put quotes around it, are quote unquote warm. So this is an example of something that is not a set. So this is not a set, and the reason is because warm is not well defined. Right? Again, we don't know what it means. How could I change this to make it a little bit better? So I could say these, so all days in 2019 with a temperature of at least, and then let's say 80 degrees Fahrenheit. Now that is a set, right? So this is a set. It's a set because I know exactly. So this is a collection of days, and this set is referring to all the days where the temperature was at least 80 degrees Fahrenheit. So I know without question whether or not June 23rd would be in this collection, or September 1st, or March 14th. All I have to do is go back and look at the records to see if the temperature was at least 80 degrees or not, right? So that should give you an example, or two examples of what we mean when we say well-defined, right? Let me give one more example, and then let's say all smart students at Indiana Tech And again, if you kind of think about it, what do you think? Set or not a set? Well, you should then ask yourself, what do we mean by smart? Is it, are you going to use GPA? Are you going to use, whether or not you're on an academic scholarship? Again, it's not clear what this is, right? So this is an example of something that is not a set. All right. Let me kind of again give you an example where I kind of tweak this and make it a little clearer. So you could say something like all students with a GPA of 3.5 or higher. Right, so at least a 3.5 GPA. Now, whether or not you would say this is a good measure of smartness, that's a different question, but this is now well defined, right? So whether you accept the fact that all students with a GPA of 3.5 or higher are smart, right? That's secondary. The thing now is, these students are all well defined, right? This collection of students is well defined because I have a clear measure as to whether or not a student is a member of this particular set, right? So this one is a set. All right. So it should be very clear when you're referring to the collection before you can mention it as a set, right? So let's talk a little bit about the notation that we will use. And again, we will use this throughout. In fact, so many courses, so many formal courses in more advanced math, you usually kind of set the stage or the groundwork with a review of sets or an introduction to the notation of sets, and that's what we're doing now. So sets are denoted with uppercase letters, right? So sets are denoted with uppercase letters. So like A, B, C, etc. And elements of the sets are denoted with lowercase letters, right? So elements are denoted with lowercase letters. So A, B, C, and so forth, right? So let's look at a couple examples of this. And let's use a set with numbers now, and I'll show you different ways that these can be written. So like A could be equal to all positive numbers less than 10 and divisible by 2, right? So this is the name of the set, and here I'm describing the set in words. I'm describing it verbally. All positive numbers, I forgot my S there, less than 10 and divisible by 2. But I can also describe this set A in a different way. And again, the notation that we use is very, very important. Sets are often denoted using these braces, right? They sometimes call them curly brackets, but they're really braces. And then here, let's see if we can list all the elements of this like one by one. So it says all positive numbers less than 10 divisible by 2. So that would be 2, comma 4, 6, 8, and it says less than 10, so I can't include 10. So then I'll close the braces, the brace like this, right? So these are two equivalent definitions of the same set A, right? Let me show you another one now. Let's define B. And let's say B is this set. 1, 2, 3, 4. 1, 2, 3, 5, 7, 9, 10. Right? And we could also define. Let's define a third set C. And some of you might remember this notation going back to basic algebra using what we call set builder notation. So you could say something like this. It's the set of all x, and this is how I'm going to write my little x from now. So I'll write my little x's like this, big x's like this. So uppercase, lowercase. So it's the set of all x's such that. And what you can do is, after the colon, give the very clear, the very unambiguous definition for what it means to be an element of this set. So like, what condition does x have to satisfy in order to be an element here? So you could say that x is even and x is greater than 0, right? Right, so x is even and greater than 0. So all of these are examples of ways that you can define sets. You can define them with a verbal description. You could define them by listing the specific elements in the set separated by commas. Or you could give this kind of set builder notation where you say, okay, it's a set of all variables x, but then x has to satisfy whatever conditions here, and there could be multiple conditions, right? Now in terms of sets differ from lists in a few ways. For one, a set is not ordered. So if, for instance, I decided to write my set A like this, 8, 6, 4, 2, it would be exactly the same, right? So sets are unordered, and in a second I'll just kind of summarize these points. The other thing too, sets, when you're listing the elements of a set like this, repetitions are ignored. So for instance, let's say I did 2, 2, 4, 4, 4, 6, 6, 6, 6, 6, and then 8, 8, 8, 8. That would also be the same set A, right? So it doesn't matter how many times you list the same element. It doesn't matter the order in which you list the elements. The set is still the same. All right. So I'll just put a little note here. Sets are unordered, right? No particular order, and ignore repetition. Right? So again, it doesn't matter how many times you list the elements. Now, we would like, so as far as some other notations, let's go back to the set A. So set A has 4 elements, 2, 4, 6, 8. Here is, so they're I'll write out again the statement verbally and then show you what the set notation is. So here's a true statement. 2 is an element of A, right? Now, and that's fine. We can write this down, but in math, we like to be concise and precise all at once. So there is a notation that we use to indicate this phrase is an element of or is a member of. Remember, element and member are synonymous when we talk about sets. So how could we write this in a more concise way? Well, here is the notation. You list the element and you do this little symbol. It looks like it's like a C with an extra line there. It looks kind of like a funny E, but that notation is used to represent the phrase is an element of, and then I put A there, right? So obviously this is a lot more efficient to write than all of this. Similarly, again, looking at A, we can see that 3 is not an element or member of A, right? Well, this happens a lot in set theory. When you have an element that or a symbol that represents some statement, if you want to negate that statement, in other words, if you want to say like not such and such, you simply put a slash through that element. So I could write a statement like this, or I could write this, that 3 is not an element of A, right? So yes, so as we go through certain parts of this course, we're going to be making use of this symbol for is an element of, or this symbol for is not an element of, right? There's some other symbols that you need to get introduced to, and that's the concept of a subset. So if A is an element of big A, and again, I am writing this because I want you to get used to the idea of the same letter but lower and uppercase representing something different, right? So if A is an element of if little a is an element of big A and little a is an element of big B, we say that A is a subset of B. So we say big A is a subset of B, right? And just like how there is a symbol to represent is an element of, there is a symbol to represent is a subset of, right? And so we write A. Now the subset symbol is like a squished C, and then it has a line below it, and then your B there, right? So this is the symbol that tells us if big A is a subset of big B. So you can write it like this, or you could write it like this. Put B first, and then switch it's now like a backward C, and still with that line there, and then an A, right? So a lot of times this is how these are read. A is a subset of B, or B contains A. Okay, so let me give you an example to illustrate these, right? So I'm going to write down 3 sets. And I'll just make these all numbers. So let's say 1, 2, 3, 4, 5. And then let's say B is 1 and 5. And then let's say, actually I'll do 3 sets. C is just 5. And then D, let's say, is 1 and 6. All right, so we have 4 sets, A, B, C, D, and let's compare them and talk about what is a subset of what. Now, we can see that A has 5 elements, right? B has 2, C has 1, D has 2. Notice both elements in B are also elements in A. So I can say that B is a subset of A. Similarly, the element 5 is in both B and A. So in fact, I can say that C is a subset of B and C is a subset of A. Right? So all of these are true. But if you notice D has one element in common with B and A, but it has another element that's not in B and not in A, and well, definitely not in C. So we could say, for instance, that D is not a subset of A, D is not a subset of B, and it certainly D is not a subset of C. So how do we write not a subset? Well, we use the same convention here as when we want to negate a statement. And negating a statement is just saying not of that statement. We just put a slash through it. So I could say that D is not a subset of A, and D is not a subset of B. And again, just for completeness, I can say that D is not a subset of C. And in fact, C is not a subset of D either, because C has the element 5 and D doesn't have the element 5. So this is also true. So there are lots of true things we could say in terms of being a subset or not. But just to give you an example, here are a few statements that are true in terms of which ones are subsets and which ones are not subsets, right? Now, let's see, one more thing I want to mention in this video. Now, you notice, so here we had, a set that had only one element. Well, it turns out there are sets that have no elements at all. So the set with no elements is called the empty set. And how is it denoted? Well, there are two ways. There's one way that I prefer. Now, if you have your braces and nothing in it to represent no elements, then that's the empty set. You could also denote it as like a null symbol. So not 0, but just kind of a null symbol. I think this is a lot clearer, especially when you're in the context of sets. All right, so that's the empty set. And I think what we will do is we'll wrap this video up now, and then in future videos we'll continue looking at some of the basic concepts, and then we'll get into some set operations that will be very, very important going forward.